Okay, let's begin. Can you hear me?
Yes.
Okay.
Can I ask some questions about homework?
Yes, of course.
The first
Wait
question,
a minute, because some people are coming.
yes. Can I send you homework via your email, but because Google Forms like only for PDFs and I don't have time to make PDF file.
I think you can send by not to me, to the assistant.
But what's his email? We don't have one.
There is a link to this email in Wiki.
I see.
If you
Thank you.
find, you can send me and I send to assistant, but it's better, of course, to send.
Okay, I will send to assistant. Thank you. And the last question
Okay.
uh, about homework.
Yes.
In the number two, we in the homework we should find subgroups of Z6,
Start.
but in the notation, Z6 doesn't have zero in the set.
Yes.
So how we supposed to find subgroups if the conditions to of subgroup isn't like
No, you have another uh, operation. The operation is multiplication, and the natural element is one unit.
but in the
Zero.
homework is uh, plus multiplication.
I'm
The neutral element for plus is
see.
zero.
Let me see your homework. Um, wait a moment. Wiki. And okay, let us see something. Here, your homework, number 2, yes?
Yes,
That's 6.
yes,
Yes, the operation is addition, and that 6 has 0 in it.
but in the notes that you have sent to us, the all z's have started from 1.
No, that there are two. Okay, let me send you a link to a dashboard, and I can write then. Um, wait a moment. Okay, I have sent you a link to the board, and now I can write. There are two groups. Let me see. Sorry. Okay, there are two groups. The first is Z, for example, 6 with plus, and the second is Z6 star, which is with the operation multiplication. There is 0 here. Here there is 0, 1, 2, 3, 4, 5, 6. And here just 1, 2, 3, 4, 5. Is it okay? Is it, do I understand it?
No, actually, can you explain why is it so?
Okay.
Once more.
I'll try to explain. There is a question. Oh, sorry. Yes, of course. I have some little bit of problem. Sorry. Okay. Sorry. Of course, not 6. Here to 5, and here 1, 2, 3, 4, 5. Okay. The definition of these groups. The first group, Z6 with plus, is just the group of reminders when we have model 6. Then reminders are all from 0 to 5. And we add numbers, then their reminders also add. So if I add, for example, 4 with 5, then it is equal to 9. And this is the same that 3 modulo 6. Okay, do you understand what group is Z6 with plus? Oh, I don't hear something. Okay, I hope you understand the left group. And the right group is another group. This is just invertible. Yes, they have joined us. This is invertible elements. Invertible with respect to multiplication. So if I try to, I'm sorry, Z star is not this. Let me erase. Because 6 is not a prime number. This star is just 1 and 5. I'm sorry. Because we want to consider just invertible elements. If we consider 0, there is no element 0 in -1. If we have 1, it has invertible element because 1 multiplied by 1 equals to 1, and so 1 is the invertible element to 1. If we have 2, it has not invertible element because 2 is an even number, and the model is even. So we can't multiply. I'm sorry. We can't multiply 2 with some number, and we can't obtain unit here. So there are just two invertible numbers, 1 and 5. And the right group is of just two elements. But if this model is not 6, but it's prime, then you have a lot of elements. Let me show, for example, Z7 with multiplication, that's 7 star. Then there are elements 1, 2, 3, 4, 5, 6. Here, there is no just 0. 0 is not in this group. So every element here is invertible, and they form a group altogether. For example, if we have 3, there is invertible element to 3. Let me think about it. 3x equal to 1, modulus 7. Now I will manage to solve this equation because I just find it among 0, 1, 2, 3, 4, 5, 6. Let me try just brute force. 0, it's not a solution. 1, 3 multiplied by 1 equal 1, no. 2 multiplied by 3 equals 6, no. 3 multiplied by 3, 9, no. Okay, somebody just says that 5 is good. We will see. 4 multiplied by 3 is 12, not 1 modulo 7. 5 multiplied by 3 is 15, so it's 1. Yes, of course, this is the correct solution. And 6 multiplied by 3 is 18, it's not 1 modulo 7. So this is the solution, and we understand that 3 is an invertible element. So these all elements are coprime with 7, and hence they are invertible in modulo 7. So the n star consists of all elements which are not bigger than n minus 1, and such that they are coprime with n. So here all elements except 0, and in case in the case of 6, there are just two elements which are coprime with 6. Okay, is it clear now?
Yes, actually for me, but I don't know how for others, so everybody say something.
Yes, it's clear.
Okay, I'm glad to hear it. I'm sorry, I think that the first seminar was not very good. In that star 13 is there an easy way to find order for 11. Okay, let us solve this problem sheet. Brute force. I think that there is a way which is brute force. So let us just answer the question from chat. We have this group, and with multiplication, of course. And we want to find order of 11. And of course, we can start with 11, then compute 11 in square, 11 in third, and so on. And once we obtain unit. And we will try it to do now. Now, after the second lecture, you understand that order of 11 divides the number of elements in this group, so it is 12. And you can use this. But in your homework, you just want to just multiply by 11. Okay, let us try. 11 in square, it's 121. So it is equal to minus 9 modulo 13. So it is equal to 4. Yes, it's equal to 4 modulo 13. Okay, then 11 in the third square. It is equal to 44. And now it is equal to, let me think, 5, yes, modulo 13. Another 11 in the fourth equals to 55. So this is equal to, let me think about it, to 1, yes? No. 39, then 40, 50, 54, yes, 54. I'm sorry. I have a problem with my arithmetic. 52, so it's equal to 3, yes. Okay, then 11 in the fifth equal to 33. It's equal to minus 6 equals to 7. 11 in the sixth power, it's 77. I'm sorry, 77 divided by 13. It's 11. Oh, it's 12. I'm sorry. It's 12. Okay. And 12 is equal to minus 1. This shows that 11 in 12 equals to unit. So now we know that order of 11 divides 12, and so it cannot be more than 6, but not 12. So the answer is 12. But in your homework, you
I'm very sorry. Can we like have our like classwork because there is no time for discussing homework again.
Okay. Let's begin with our seminar 2, of course.
Yes.
Thank you. And could you actually send the link to the problem sheet?
It's on wiki.
Oh, okay.
It's
Thank you.
always
And
would be on Wiki.
actually, some people wanting to like to attend the seminar. Can you like invite them? They have.
Yes, I have just did this. Okay, let's begin with our second. Let me show. You have not see because it is not in browser. Okay, the first problem from this paper is find left and right cosets of this subgroup in S3. Okay, I'm sorry. I need to. Okay, now you can see it. And this subgroup is two variants for sigma. The first is that sigma is just transposition 1 and 2. Okay, let's begin with it. What is left cassettes? Left cassette, when we have a group G and a subgroup H, then left cassettes are G multiplied by H big, and this is just G multiplied by all H, where H comes from H big. Okay, just what is the subgroup sigma in angle baskets? This one. This is the cyclic subgroup given by sigma. Cyclic subgroup, it means that this consists of all powers of sigma. But sigma squared, squared, sigma squared equals to identity permutation. So there are just two elements in this group. This is identity element and our element. I think I must.
Question.
Yes.
Why did you mention that sigma squared is identity, and how do you know this?
Okay, let me remind that this is just cycle. What does it mean? This notation means that 1 goes to 2, 2 goes to 1, and since we live in S3, then we have 3 which goes to itself. It corresponds to the following permutation. 2 and 1 goes to each other, and 3 stay on itself. How to multiply sigma by itself? You just need to rotate all the cycles in power 2, so 2 times. 1 goes to 2, and when we rotate it the second time, it goes to 1. So 1 goes to 1, and this means that 1 in sigma squared stay to itself. So for 2, this situation is similar. 2 goes to 1, and in sigma squared, it goes to 2. And 3 is much simpler. 3 goes to 3, and then again 3 goes to 3. So we have that sigma squared equals to
Yeah, okay.
okay. So now we just by brute force will go through all of the group S3 and describe all left cassettes. So the first element is identity. I will say that sigma in angles equals to identity and 1, 2. So identity, I'm sorry, I will do it just. Identity multiplied by this H. What is it? I need identity multiply to identity. Of course, I have identity. So, and I need identity multiplied by 1, 2. Of course, I have this permutation. So this is equals to identity and 1, 2. And so it equals to H. Then I need, for example, this left class. What shall I do? I shall multiply 1, 2 to their identity. Of course, I have this one. And the second element is 1, 2 multiplied by 1, 2. So I have identity. These sets are coincide. So these left cassettes coincide. Okay, let's proceed. I have this permutation in S3. So let us think about this left cassette. 1, 3, I multiplied to identity. I have 1, 3. And then 1, 3, I multiplied by 1, 2. Let me do my multiply. Let me multiply it here. To multiply permutation, I need not send it to the normal form. I just can multiply it by cycles. So let us think. First, we do the right permutation. So 1 goes to 2. And then here in the left permutation, 2 goes to 2. So as a result, 1 goes to 2. Okay, 2 goes to 1, and here 1 goes to 3. So 2 goes to 3. And 3 stays here and then goes to 1. So the cycle is over. So 1, 2, 3 is here. Is it clear for now?
Yeah, pretty much.
Okay. I proceed. When I have 1, 2, 3 multiplied by h, I obtain 1, 2, 3, of course. And then I need 1, 2, 3 multiplied by 1, 2. Here it is. It's easy to see that I have 1, 3. So I have the same left cassette. And this is not an occasion, this is the rule, because you have a theorem in your lectures that if two left cassettes are intersects, then they coincide. So If I take an element 1, 2, 3 from this left cassette, then it is in its own cassette. So this cassette, of course, there is an element 1, 2, 3 in it. And then these two cassettes, this one and this one, are coincide. So this left cassette coincide with this. Okay, and the last one is 1, 3, 1, 3, 2, 3 multiplied by h equals to 2, 3, of course. And I need some multiplication. 2, 3 multiplied by 1, 2. It is equal to, let me see, 1 goes to 2 and 2 goes to 3. So 1 goes to 3. 3 stays here and then it goes to 2. So, and 2 goes to 1 and then 1 stays. So we obtain 1, 2, 3. 1, 3, 2, I'm sorry. And this is the left cassette of 2, 3. And of course, this coincides with left cassette of 1, 3, 2, H. So we obtain all left cassettes. There are 3 left cassettes. Each of them is of 2 elements. Is it clear?
Yeah, but you do it so fast. I don't know really how, but that's okay.
And the same deal we will do when we describe right cassettes. The only difference that we multiplied not from left but from the right. Okay, let us begin with it. We have an element, the same situation. Identity and 1, 2. And now we need to describe right cassettes. So let's begin with this one. Of course, it equals to H is the subgroup. Of course, it is equal to H and it is equal to right cassette of 1, 2 because there is the same assertion for right cassette. If they intersect, then they coincide. So the second one is H multiplied by, for example, 1, 3. I just take one of the elements from S3, which doesn't belong to this cassette. Okay, let's try to understand what elements are here. 1, 3, of course. And the second one is 1, 2 multiplied by 1, 3 from the left. On the right, 1 goes on the left permutation, 3 stays. So 1 goes to 3. On the right permutation, 3 goes to 1, and then 1 goes to 2. So 3 goes to 2, and 2 stays in the right permutation, and then goes to 1. The circle is over. So 1, 3, 2. And of course, these right cassettes coincide with h multiplied by 132. And here is the difference, because let us see the left cassette of 1,3. The left cassette of 1,3, it is here, and it consists of 1,3 and 1,2,3. And now let us see the right cassette. So the right cassette consists of 1,3 and 1,3,2, not 1,2,3, but 1,3,2. This is the difference. So left and right cassettes doesn't coincide. And the last one is 1 multiplied, for example, 2, 3. And it equals to, let us see, 2, 3. And I need not solve what is the element of this cassette, because there is just one element of S3 which is not in this and in this, and which is not here. The last element is 1, 2, 3. There are 6 elements in S3, so the last is 1, 2, 3, and it must be here. And this left cassette equals to h multiplied by 1, 2, 3.
So when we like find all the cassettes, all the results that we got from finding all the cassettes must like make up the whole space, or what?
Yes, we have just all the group, and it divided to left cassette and some another way which it divided to right cassette. But all of the
It's
group,
the same group.
this is the same group, but these cassettes are not the same. Let me show it in our example.
And we don't really care about what is our age. It always works, right?
It always works because, let me show it, because every G belongs to GH. So every G is in some cassette. Okay?
Mhm.
Okay, and let us just give a picture what we have. We have S3. There are 6 elements in it. 1, 2, 3, 4, 5, 6. And there are two way to, okay, just these 2 elements is our age. And this is our age. It is equal to, for example, identity multiplied by age, and it is equal to age multiplied by identity. So one of left cassettes coincide with one of right cassettes and coincide with age. This is the common rule. And then we divide it into left cassettes. There are 3 left cassettes, each of them of 2 elements. And the other way we divided to right cassettes. The picture is this. So one of left cassette coincide with right cassette, but the other one don't coincide. Okay? Do you understand what is the picture? Is the picture is clear?
Yeah, pretty much.
Okay, thank you very much. Uh, I don't want to solve the point B. So let us begin with the second problem. Oh, just me. I want to say a few words about point B. So here sigma equals to 1 to 3, and the cyclic group generated by sigma equals to identity 1 to 3 and 1, 3, 2, which is equal to sigma squared. And this is equal to sigma third, because sigma is just a cycle with length 3. So we have that the group S3 consists of 6 elements, and the subgroup H, which is equal to cyclic group generated by sigma, it consists of 3 elements. So what is the picture? We have 2 left cassettes. The first left cassette is just identity multiplied by H, the H itself. And the second is all the others. And right cassettes are the same, because we have no other elements. We just have just one cassette except H. So in this picture, left cassettes and right cassettes coincide. Okay. Okay, now let's deal with the second task. So we have G equals to S4, and H equals to such sigma that sigma of 4 takes 4 to 4. And so we need to describe its left and right cassettes. Okay. What is the left cassette? For example, if we have, for example, this one. No, this one, it's not interesting. When I have identity, then identity multiplied by H, because of course equal to H. This is one of the left cassettes. If I have an element from H, if H belongs to H, then of course H multiplied by H equals to H, and we have the same cassette. So what is the simplest element which does not belong to H?
Wait, can you like explain once more the last thing that you wrote?
The last, this one.
What's H belongs to H, and then H by H is H?
If H belongs to H, then we multiply H to HB. What is the result? The result is H multiplied by H hat, where H hat goes through h big. So when I multiply all the elements from h big to h little, I have all the elements from h big, but in the
Just
other
like
order,
moved a bit. Yeah.
just
Okay.
permutation of all elements.
Okay.
Because if I have,
And
for example,
here, H small is also all the elements of H.
yes, here we begin with h belongs to hb. So
Yeah. Right. Okay.
uh, and now give me the simplest element which doesn't belong to hb.
1, 2, 3, 4.
No, for example, 1, 2, 3, 4. Maybe this is not the simplest, but
Maybe.
this is rather good. And let us think about what is the uh, left cassette of this element 1, 2, 3, 4 multiplied by h. I interested if there is a permutation delta from this left cassette. What can we say about delta of 4?
It equals to 1.
It equals to 1 because what is delta? Delta equals to 1, 2, 3, 4 multiplied by some sigma, where sigma belongs to hb. And then if we think about this permutation, where this permutation takes 4, sigma takes 4 to 4 because of definition of h. And then this permutation takes 4 to 1. So delta from 4 equals to 1. So what is the hypothesis that 1, 2, 3, 4 multiplied by h equals to all permutations delta such that delta from 4 equals to 1.
Okay, it's understandable.
Let us prove it. We want to prove it. Is there some ideas how to prove it?
Like, what do we actually need to prove?
The assertion on the left bottom angle. This
Yeah, I
one.
get it, but we have just like explicitly shown that 4 always goes to 1.
Yes, we explicitly show that 4 goes to 1, but we need to show that all these permutations are in one coset. This needs some.
But we don't have any knowledge about sigma itself and delta because of we don't have the knowledge about sigma.
We have the following knowledge. We have knowledge that what is the order of this one, the order of left cassette. I claim that this equals to the order of h. Yes, of course, there is a right answer in chat. So how many elements in H? Let us think about it. These elements is some permutation which takes 4 to 4. This is 3 factorial, so 6, 1. Okay, And how many permutation takes 4 to 1? Of course, the same quantity. So 6
And it's enough for the proof, right?
enough for the proof. Yes.
Great.
Okay, what is the other left cassettes? How many left cassettes and what are they? Of course, if we know that the order of H equals to 6 and the order of S4 equals to 24, then we understand that there are just 4 cassettes, 4 left cassettes and 4 right cassettes.
That's why?
Because all of the group consists of left cassettes, they don't intersect, and each of them is of 6 elements. Okay.
Again, like, why? That's because like when we get, like if we're trying to find the coset that coincides with something out of H, it's the same. Like again, I just didn't get the logic why there's 4 cassettes.
Okay, we have a group which consists of 24 elements, and it divided into some of cassettes,
Yeah,
and
okay.
each of them is 6, of course.
Yeah, I get it.
And now, can you guess what is the other cassettes are? We have 2 cassettes. The first is just sigma, which takes 4 to 4, and we have another one. It's just delta, which takes 4 to 1.
So the other 3 that take 4 to 2, 3.
Of course, I have no another lattices, so I just write sigma 2 and 3. And it's reasonable because, for example, if we have one permutation which takes 4 to 2, for example, this one, I'm sorry, I will take another color and I will write here. For example, 2, 4. If we have this cassette, this is just all sigma, which sigma of 4 equals to 2. So the proof of this is the same that the proof of that 1, 2, 3, 4 multiplied by H coincide with this one. And for example, 3, 4 multiplied by H equals to the last left cassette. Okay, and now let us think about right cassettes. If we have H and we try to understand, of course, if we have an element H from H and we consider this right cassette, it is equal to H big. And now let us try to understand what is the right cassette H, for example, to this one. Let us think about it. So we have an element sigma from here, and let us think about sigma multiplied by this one. This is some delta, and do you know some properties of delta? But for example, I wonder what is delta of 1. Somebody have right that this is 4, and of course this is correct. Yes, because delta, first of all, we take 4 to 1 by this permutation, and then sigma takes 4 to 4, and so on. 1 as a result goes to 4. And of course, this is the characterization of this right cassette. So I want to prove that this right cassette coincide with all delta such that delta takes 1 to 4. Let us prove it by such way. If we have delta from here, then delta equals to some sigma multiplied by 1/4. What is the sigma? Sigma is, sorry, sigma equals to delta multiplied by 1/4 in minus 1. So sigma equals to delta multiplied by 1/4. And if we have a delta from here and we multiply it by 1/4, then of course this sigma takes 4 to 4 because 4 goes to 1 first of all here, and then delta takes 1 to 4. So in the sigma, 4 goes to 4. So sigma belongs to H. Let me write it down. Sigma belongs to H. And so we understand that every delta from this set can be obtained as sigma multiplied by 1/4. So this is, we prove this equation. Of course, the other right cosets can be constructed by the same way. Okay, let us proceed with this third problem if it is clear. Is it okay? Clear?
So all the right cassettes are going to be some deltas where 1 goes to 4, where 2 goes to 4, where 3 goes to 4.
Of course, yes.
And all the others that are like the same as H.
Yes, and you understand that right cassettes and left cassettes are not the same because let us see. first left cassettes was 4 goes to something, and right cassettes is
Something goes to 4.
Okay, the third problem is
Excuse me, could you also repeat how do we prove that H is a subgroup?
that H is the subgroup.
Yes.
We're given that, I guess, yeah.
No, we need to show that H is a subgroup.
Let me see.
Oh, yeah.
I'm sorry, I just have not shown that H is subgroup. Let us show it. Okay. We have H. This is all sigma such that sigma takes 4 to 4. Let us try to show that H is subgroup. What we need to show? We need to show that if we have 2 elements, delta and sigma from H, then their multiplication belongs to H. This is true because sigma takes 4 to 4 and then delta takes 4 to 4. So the product of sigma and delta takes 4 to 4. And the second one is that identity belongs to H, so the neutral element of the group. This is correct. And the last one is that if sigma belongs to H, then sigma in -1, the inverse element, belongs to H. Okay, how to obtain the inverse element? We need just these 2 rows transpose just the first row is becomes the second, and what is sigma? Sigma is just an element of H here, or this maybe here this is sigma in S4. Okay, and if we change these 2 rows, then of course 4 goes to 4 in sigma -1. If this is sigma from H, then this is sigma -1 and it belongs to H, so this is true again. So this is the proof that H is a subgroup. Is it clear?
Yeah.
Okay. The third task is that if we have a group, a multiplicative group of complex numbers, and we have H equals to Z such that the model of Z equals to 1. We need to show that H is normal subgroup. The normal.
What is normal again? Can you?
Yeah.
Okay, there are 4 definition of normal subgroup which are equivalent one to each other. Let me write it down. So the first is that left cassettes equals to right cassettes.
Oh, so if the group itself is commutative, it produces normal subgroups.
Then every subgroup is normal.
Oh, okay. Understandable.
Okay, this is that GH equals to HG. For example, we have seen that this one is not normal in S3. Yes, normal we write by this triangle, and if it is not normal, just we remove this triangle. So the second one is that G minus 1 equals to H. And the third is the most convenient to check, is that for every H from H big, we have G multiplied by H multiplied by G inverse belongs to H big. This is very convenient because there is no big sets, but there is an element here, and it's rather convenient. And the last is that G minus 1 is a subset of H. The second one is that there is equalities here, and the inclusion in the last. So the main would be this one. Let us show that this is a normal subgroup. So you have said already that when all the group is commutative, then every subgroup is normal. So we need to show that this is a normal subgroup. Oh, I'm sorry. Why there is no... you have not seen what I write. Now it's okay. So we need to check that this is a normal subgroup. We need to check just this that this is a subgroup. Okay.
Again, could you repeat it?
Since the multiplicative group of complex numbers is a commutative group, then every subgroup is normal, because right cassettes, left cassettes are the same. Okay, so we need not prove that this subgroup is normal. We need to just show that this is a subgroup. Okay.
Yes, seems right.
Okay, let us show that this is a subgroup. We need to show 3 points. The first point is that if we have Z with model 1 and we have, for example, T with model 1, then the multiplication has model 1. Yes, this is a well-known property of complex numbers. The second, then, the neutral element, which is 1, belongs to our subgroup. Yes, because the model of 1 equals to 1. And the last, if Z belongs to H, so the model of Z equals to 1, then we need to show that the model of the inverse element equals to 1. Yes, this is of course correct one, because the model of inverse element is 1 divided by the model of Z. So all the properties are correct. So this is a subgroup, and the fact that this is a normal subgroup is obvious because all the group is commutative. Okay, let's proceed with another not so elementary. Let us solve the number 7.
Excuse me. And what about the cosets?
Ah, I'm sorry.
Yeah, we have to find them, and it's like seems
yes.
strange.
Of course, cassettes. Let's find the cassettes. What is the cassettes? We have G, and we multiply it to our H. This is left cassettes which coincide with right cassettes. So this H is all Z such that model Z equals to 1. What is this set is? We have 1G and we multiply it by Z. What is the model of this one? The model is of this one is equal to model of G multiplied by model of Z. So this is equal to model of G. And if we have, so our hypothesis that this one equals to, to all x from C star such that model of x equals to model of G. Let us prove it. We have proved that that there is an inclusion here. Why there is the inverse inclusion? Because if we have x such that model x equals to model G, then we need to show that x equals to GZ. So Z equals to x G minus 1. And if model x equals to model G, then it implies that model Z equals to 1. So this is this shows that there is inverse inclusion, and we have that. Let me show bullet picture.
Again, could you repeat the explanation for the last line that you wrote?
Of course, yes.
What do we prove and how do we prove? Okay, because I didn't catch like the logic.
Okay, we prove the inclusion that this guy is in this guy. So can we how we try to prove it? We try to prove we take x from here, so model of x equals to model of G. And we need to show that x equals to GZ, where Z is from H, so model of Z equals to 1. Of course, if this equation is correct, then Z equals to x G minus 1. But since model of x equals to model of G, then we obtain that model of Z equals to 1, and hence Z belongs to H. So we start with x from here, and we show that x equals to g multiplied by z, and so we are here. Okay.
All right, I guess.
And in the picture, our H is all elements with model equals to 1. This is a circle. And all the other cassettes are another circle with the same center on the origin. So these circles are left cassettes, and they are right cassettes. Okay, let us solve the number 7. Number 7, we have two subgroups. The first two groups. The first group is GLN of R. It is just general linear group, all matrices with non-zero determinant, so all non-generated matrices. And the subgroup is S and this is all matrices with determinant equal to 1. And we need to show that SLN is a normal subgroup, so that we can stand this triangle. This triangle shows that just by definition that the right one is a normal subgroup of the left one. So how shall we prove? We take an H from here and G from here. And we need to show that GH, G minus 1 belongs to H. H is the subgroup.
Wait, didn't we have to prove that GH equals to HG?
Okay, we will use not the first one here, the third point here. All the points are equivalent. That was shown in lectures. And we want to use the third definition of normal subgroup. Okay?
Mm-hmm. Okay.
So let us show. What does it mean that this element, this matrix, belongs to H? This is equivalent that determinant of this one is equal to 1, because H consists of all matrix with determinant 1. But this determinant, it's well known that this is the multiplication of det G multiplied by det H multiplied by det G minus 1. Okay? And this one and this one are inverse. And the middle one equals to 1. So, okay, we obtained that this is equal to 1. And hence, this belongs to H. So we showed that this is a normal subgroup. Is it clear?
Yes.
Okay, and now I want to solve the fourth problem. We need to describe all the subgroup in Zn with addition. let us show that this is a cyclic group. Let us show that each subgroup in this group are cyclic, and each subgroup is cyclic, and it is just a subgroup generated by D, where D is a divisor of N. Okay, let us show it. We have some subgroup H in our group. So there are some elements. We want to take the minimal of these elements, because this group consists of 0, 1, 2, 3, so n minus 1. Some of them are elements of H, and 0 is the element of H. 0 belongs to H because of H subgroup, and the neutral element must to belong to H. So there is the minimal except 0 element which belongs to H. Let it would be K. Let K is the minimum element of H except 0. And oh, I'm sorry, there is already, I have already the lattice D. This is the same lattice, so let D be the minimum element of H. Now let M be any other element of H. Let us go to the following frame. Okay, M is an element of H, and D is the minimal element of H. So we can divide M to D with remainder. So M equals to D multiplied by Q with plus R. And R is not bigger than D. So, but this guy belongs to H. This guy is equal to D plus D many times, and each D belongs to H, so it belongs to H. And this is the subtraction of M and DQ, so this belongs to H. And this is the contradiction with the definition of D, because D is the minimal element of H, but R is not bigger than D. I'm sorry, not bigger, but it is just smaller than D. So we have a contradiction. The only way we have not a contradiction if R equals to 0. So M is divisible by D. We prove that M is divisible by D. So H, let us see on the second frame. We have H. 0 belongs to H, D belongs to H, 2 multiplied by D belongs to H, 3 multiplied by D, and so on. if we have another one, then we have showed that every m which is in H, it is divisible by D. So all the elements are divisible by D. So, but there is n and n. If we have k multiplied by D, and then we have k plus 1 multiplied by D, which is bigger than n, and this is smaller than n. Then
Excuse me. What is k here?
k is the last one, which is smaller than n. So
Then what? Then
then
okay.
k multiplied by D is smaller than n.
I get it.
Then we have an element n minus kd, which is, this is 0, and this belongs to H. So this element belongs to H. But it is just an element which is smaller than D. This is a contradiction, and the only one, I'm sorry, where is